Interference using Lloyd's mirror. Interference fringes are produced using Lloyd's mirror and the source S of wavelength lambda equals 606 nanometers as shown in the figure below. So we have a source here, 606 nanometers, sending a beam to point P, that's the red one, and it's at a distance L with respect to the viewing screen. Fringes are separated by delta y is equal to 1.2 millimeters, formed on a screen at distance L 2 meters from the source. Find the vertical distance h of the source above the reflecting surface. No calculators are allowed, and L is much greater than h, so we have the parallel ray approximation. Okay. So why do we have an interference pattern? An interference pattern is formed by the beam coming from the real source S and the virtual source S prime. So where is the virtual source? We have the real source S, the image of this source on the other side at a distance h with respect to the mirror. We have a virtual source S prime. So we have a beam coming from the virtual source, that's the blue one, and the beam coming from the real source, that's the red one. And that coming from the virtual source is actually a reflected beam from the mirror. So the beam from S prime is the reflected beam from Lloyd's mirror. So if you have a beam that is reflected from Lloyd's mirror going from a medium of low index of refraction to a high index of refraction, here we have a 180-degree phase shift in the reflected light. So it's 100-degree phase shifted. Remember that in the lectures we said this is analogous to having waves on a string reflecting from a fixed end. Okay, or reflecting from a medium, another string with a heavier mass per unit length, a larger mass per unit length. Now, since we have L, the distance to the screen, much greater than h, or 2h, that's the distance between the real source and the reflected source, parallel ray approximation holds. So we can write the path difference between these two rays. The path difference, just like in Young's double slit experiment, will be, if this is the angle theta with respect to the horizontal axis here, these two rays are approximately parallel. So this angle is theta, this angle is theta. The angle from the mirror towards the point P is theta, so this angle is theta. Then we have theta 90 minus theta, 90 degrees theta here, 2h sine theta, the path difference between these two occurring right here, and then the two rays are traveling the same distance. So that path difference, delta, is equal to 2h sine theta. What is the condition for constructive interference? We can write the condition for constructive interference. Now we have a path difference 2h sine theta. But one of the rays is 180 degrees phase shifted. Normally we would write path difference equals m lambda for constructive interference, but because we have a 180 degree phase shift, this should be m plus 1/2 lambda, where m can take values 0, 1, 2, etc. In addition, for the pattern on the screen, the central point normally would be a maximum. Instead of a central maximum, we will have a central minimum. Okay, so tangent theta, if you look at tangent of this angle theta, it is y divided by L, the distance to the screen. So tangent theta is y over L. And when we look at this pattern close to the center, we're looking at small angular displacements. So tangent theta should be approximately equal to sine theta. We have the small angle approximation. So where is the first maximum? First maximum is when m is equal to 0, we will have 2h times sine theta, while sine theta is equal to tangent theta, so it's going to be y0 over L, m equals to 0 gives me lambda over 2. Second maximum I will observe at 2h, now m is equal to 1, y1 over L equals 3 lambda over 2. So if you look at the difference, you will see that 2h times y1 minus y0 divided by L is equal to 3 lambda over 2 minus lambda over 2, which is lambda. So what does this tell us for h? H is equal to lambda L divided by 2 delta y, where delta y is y1 minus y0. That's the distance between fringes. Fringes separated by 1.2 millimeters. Okay, so let's plug in the numbers here. The wavelength is 606 nanometers. 606. The L length is 2 meters, so 606 to 10 to minus 9 meters, divided by 2 delta y, 2 times 1.2 millimeters, 1.2, 10 to minus 3 meters. Now you can see that these 2's will cancel. Alright, and we have 1.2 and 606, so this is going to become when divided by 6, 0.2. This is divided by 6, becomes 101. And as a result, I find h is equal to 1 over 0.2 is 5. 505, 10 to minus 6 meters. And we can write this as h is equal to 5.05, 10 to minus 4 meters. I keep 3 significant figures here because all the numbers are given with 3 significant figures. Okay, so finally we can summarize this solution. We have a source of light on one side of a mirror at a distance h, perpendicular distance h from the mirror. And because there will be an image of this source on the other side producing this reflected ray, this reflected ray and the incident ray, incoming ray from the real source, will interfere to form an interference pattern on the screen. But one thing we should be careful with, the reflected light is 180 degrees phase shifted. It's analogous to mechanical waves on a string going from a light string towards a heavy string. This is going from low index of refraction to high index of refraction medium. So with this 180 degree phase shift taken into account, the path difference between the rays coming from the real source and the virtual source is 2h sine theta, where theta is the angle with respect to the horizontal of these two rays. And since L is much greater than 2h, the parallel ray approximation holds, so these angles are approximately the same. And tangent theta is y over L at the same time. So the condition for constructive interference, the path difference normally would be equal to m lambda for constructive interference, integer multiples of a wavelength, but because of this 180 degree phase shift, this becomes m plus 1/2 lambda, and the central maximum turns into a central minimum. Close to the center, when we look at this interference pattern, tangent theta is equal to sine theta, small angle approximation. First maximum occurs for m equals 0, 2h y0 over L, because tangent theta is replacing the sine theta here, is lambda over 2. M equals 1 gives 3 over 2 lambda. That's 2h y1 over L for m equals 1. And 2h y1 minus y0 over L is 3 lambda over 2 minus lambda over 2, that's lambda. So this gives us h equals L lambda over 2 delta y. When we substitute the numbers, we find 5.05 10 to minus 4 meters. And here we should have 3 significant figures, as all the numbers are given with 3 significant figures.